Okay guys, so here's this guide video for the problem. So it asks you to consider this differential equation. On the axes provided, sketch a slope field for the given differential equation at the 9 points indicated. So I did, a table for all 9 of the points, and I got the slopes already just to save time. Now, so as I've said before, the zero slopes need to have little horizontal lines. The positive slopes need to be positive, negatives need to be negative, and then the relative steepness needs to be clear. So, all right, well, so at 0, 1, I've got a slope of 0. Okay, at -1, 0, I've got a slope of -3/2. All right, looks like 3/2 is going to be my steepest slope. So at -1, 0, so I want to be going down 3, right 2, kind of, yeah. So that would be like about 3/2, I guess. And then for -1, 1, I want to go down 1, right 2. Yeah, so using that little trick with the dots, guys, does help you with the relative steepness. It helps me anyway. All right, and then 1/2 at -1, 2. So up 1, right 2. And then at 0, 0, I want to have a slope of -1. So down 1, right 1. Okay. And then at 0, 1, I had that slope of 0. At 0, 2, I have a slope of 1, up 1, right 1. And then at 1, 0, -1/2, down 1, right 2, about that. 1, 1 is +1/2, up 1, right 2. And then +3/2, up 1, 2, 3, right 1, 2. Yeah, that looks pretty good. All right, so I'm done with the first part. Now find d²y/dx² in terms of x and y. Describe the region in the plane in which all solution curves to the differential equation are concave up. Okay, so concave up, I want y double prime to be greater than 0. That's what I want. So yeah, I'm going to take the first derivative and I'm going to take the derivative of it. So y double prime is 1/2 plus y prime. And then I got to plug this, y prime back in for itself. This ends up being -1/2 plus 1/2 x plus y. Okay. All right, now, just like before, we're going to first find where the second derivative is 0, and then, so that'll be like a boundary line. And then, on either side of that boundary line, we're going to pick a testing point to plug into the second derivative and see if it's positive or negative. So, -1/2 plus 1/2 x plus y equals 0. Let me find the boundary line. So y is -1/2 x plus 1/2. So let's just do like a sketch. So the y-intercept is 1/2. And then the slope is down 1, right 2. Down 1, yeah, about that. All right, just a sketch is fine. All right, so this line here is that. Now, I'm going to pick a point. It's nice, guys, if you could pick a point like on an axis. And if you look here, guys, 0, 0 is below the line. So I'll use 0, 0 as my testing point below the line, the boundary line. And then I'll use like 0, I can even use 0, 1. I look like I'm up pretty high though, so I'll use 0, 3. So over here, I'll say d² y/dx². evaluated at, let me do 0, 3 first. And then this is the second derivative. So this is going to be negative a half plus 3. That's greater than 0. And then d squared y over dx squared evaluated at 0, 0. That is negative 1/2. That's less than 0. So concave up, concave down. So the points at which the solution curves are going to be, or the region in the plane where the solution curves are going to be concave up, is all of this. It's just like an inequality, guys, just like you've done before. So concave up. Okay. And then here's the description. All points x, y, for which y is greater than, so I'm above the line, so it's greater than. If I were below the line, it would be less than. For which y is greater than negative 1/2 x plus a half. They don't actually say to explain. I don't know. I'll just say, I mean, I showed work. I'll say because dx squared greater than 0 for these points. Okay, I think that's good enough. Okay, but when you're describing the region in the plane, that's how you want to say it. You want to say all points x, y for which all right. Yeah, they didn't say to give a reason that time, though. So we didn't actually have to. You would have been fine, I think, just with that. All right, now for C. Part C, let y equals f of x be a particular solution to the differential equation with initial condition here. Does f have a relative min, a relative max, or neither at x equals 0? So this is part C, and I've said this before, but let me just summarize. Okay, so min, we would want y prime equals 0, y double prime greater than 0. Okay, horizontal tangent concave up means min. Max, we would want y prime equal to 0, y double prime less than 0. Horizontal tangent concave down means max. So I've got to take f of 0 equals 1, and I'm going to plug them into the first and second derivative. So dy dx evaluated at 0, 1 gives me 0. Okay, so I've got that. Then I'm going to do d squared y over dx squared evaluated at 0, 1. Okay, so it's right here. Wait, no, where is it? Here's the second derivative. There's the second derivative right there. So it's negative a half. It's negative a half plus 1/2 times 0 plus 1. So this is positive a half it ends up being, which is greater than 0. Okay, relative max. No, relative min. Relative min because dy dx equals 0 and is greater than 0. Okay. Here we go. All right, now for part D. All right, so this is part D here. Find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. All right, so this is going to be very much like we did before. So I'll say y equals mx plus b. Well, if that's the case, then y prime is m, and y double prime equals 0. So I'm going to plug my y prime in, which they gave me to begin with, plus y minus 1 equals m. I'll plug y double prime in, which I found. What was it? It was negative 1/2 plus 1/2 x plus y equals 0. Okay, then I'm going to plug mx plus b in for the y's. 1/2 x plus mx plus b minus 1 equals m. Mx plus b equals 0. Okay, I'm going to solve for b in this equation. And then I'm going to plug it in over here and hope that stuff cancels. 1/2 x plus mx plus 1/2 minus 1/2 x minus mx minus 1 equals m. Okay, 1/2. All right, so that was b right there. And then things do cancel. So these 1/2 x's cancel, the mx's cancel. So you have 1/2 minus 1 equals m. So you have m is negative 1/2. Okay, now we just need b. So b equals 1/2 minus 1/2 x minus negative 1/2 x. 1/2 minus 1/2 x plus 1/2 x. So both of these cancel, and b is 1/2.